Okay, so now we are going to talk about functions of several variables. So we'll start with functions of two variables. A function of two variables, so z is equal to f of xy, maps each ordered pair xy in some subset, we call it capital D, of R2 to a unique real number z. The set D is going to be the domain of the function, and the range of f is a set of all real numbers z for which there's at least one ordered pair xy such that z is equal to f of xy. In other words, the range is basically all possible values of f of xy of our function. And this is kind of illustrated in figure 4.2 of the textbook, which I reproduced below. Notice that a function of two variables has two independent variables, x and y, and one dependent variable, z. A graph of a function of two variables is therefore going to be a surface in three-dimensional space. So let's do some examples. Let's find the domain and range for the three functions below, and let's graph z equals f of xy. So for the first function, where f is 12 minus 3x minus 4y, right? This function is defined for all x and y. And so what does that tell me about the domain? The domain is all of R2. What about the range? Well, the function can take on any real value, right? Whatever we put in, we're going to get out a real number. And so that means the range is also R. Well, I guess it's not also R, but the range is R. Okay, for the second function, we have square root of x plus square root of y. So in this case, right, the function is only defined if x is greater than or equal to 0 and y is greater than or equal to 0, right? So in other words, we have the first quadrant in the xy plane. So the domain is basically saying the first quadrant in the xy plane. Okay, what about the range? Well, the range is only positive numbers, well, greater than or equal to 0, I should say. And so the range is z has to be greater than or equal to 0. Okay, for that third example, we have the natural log of the quantity 9 minus x squared minus 9y squared. So first of all, we know we can only take the logarithm of a positive quantity. So this function is going to be defined only if 9 minus x squared minus 9y squared is positive, or in other words, we can write this as x squared over 9 plus y squared is less than 1. So another way to say this is that the domain is the interior of an ellipse, specifically that ellipse, in the xy plane. And finally, the range. Well, we know logarithms can take all positive and negative values in the range of the logarithm. So we know that is minus infinity to infinity, or R, all of R. So the graphs of these functions I generated using Maple. So example 1, if you'll recall, was f of xy is equal to 12 minus 3x minus 4y. The second example was f of xy is equal to the square root of x plus the square root of y. And the last example, the weirdest looking one, is z, or f of xy is 9 minus x squared minus 9y squared. So I guess I should actually put z equals, because it just hanging out by itself, we're not really doing much. All right. There's another topic or another thing associated with these functions of higher variables, and that's something called level curves. So if you look at a topographical map, right, we see curves that are called contour lines, and they indicate how steep the terrain is. The level curves, also called the contour curves of a function of two variables, f of x, y, those guys are analogous to the contour lines on a topographical map. So, by definition, given a function f of x, y, and a real number, call it c, a level curve of the function for the value c is the set of points satisfying the equation. Set of points, I should say x, y, right? Because we're looking in the x, y plane. Set of points x, y satisfying the equation, well, what you'd expect it to satisfy. That is, f of x, y is equal to c. Okay, give me 1 second. Let me fix the word satisfying so that when you're looking at your notes again, or if you're looking at my posted version, you don't go, what's that word? All right, so again, notice that all level curves are in the xy plane. So let's do an example. Let's find the level curves of f of xy equals the square root of the quantity x squared plus y squared. Okay, and we're going to sketch a few of them. So we have that square root of x squared plus y squared equals c, also known as x squared plus y squared equals c squared. But c has to be greater than or equal to 0, of course, because c is really the square root of x squared plus y squared. So the level curves, they're just going to be circles of radius c centered at the origin, or 0, 0 if you prefer. And so again, I used Maple to create these so that I wasn't drawing them, and they look a lot more like circles. Each level curve, by the way, can be thought of as intersecting the surface given by my z equals f of x, y, and a plane z is equal to c. So level curves are not the only way to get a two-dimensional view of my three-dimensional surface, and their other views are called traces. And so they're similar to contours. So a vertical trace, of a surface is a curve that represents the intersection of the surface with the plane x equals a. So in other words, a vertical trace is the curve f of a comma y is equal to z, and that is going to be in the yz plane, and or with the plane y equals b. So in other words, in that case, we have the curves, actually, because there are infinitely many. But anyway, the curve f of xb is equal to z, and that one's going to be in the xz plane. And so that's the idea. So as an example, let's sketch the vertical traces of f of x y equals 8 minus 4x squared minus y squared for a, x is equal to 1, and b, y is equal to 2. So for the first one, for x is equal to 1, right, we are looking at, well, f of 1y, are 8 minus 4 times 1 squared minus y squared equals z, or z is equal to 4 minus y squared. Now you should recognize that as a parabola. And if we're in the yz plane, it's a parabola that is pointing down in the yz plane. And so a parabola, might be nice if I wrote this, in the yz plane. By pointing, I meant open. In the yz plane with, and its vertex is 0, 4, and it opens downward in the yz plane. Okay, B. So if y is equal to 2, then we're looking at f of x2, which is equal to 8 minus 4x squared minus 2 squared, and that has to equal z. And so that one's going to give us z is equal to 8 minus 4x squared. So again, we have a parabola in the xz plane. Xz plane with vertex, well, in this case, the vertex is going to be, I believe it's 0, 8, and it's open down. Okay, now there's two ways to draw these in Maple or anything else. Well, you might be able to do it in Wolfram Alpha, but the way I drew them is to sort of emphasize the plane intersecting with the surface, and I used GeoGebra for that. So our surface, and then it is sort of the, well, the three-dimensional thing. The plane is the intersecting it, and then the outline of that blue shaded region, that gives us our level curve. So next time we are going to, well, do we have time? Well, might as well, we're not going to say much. We can also define functions of any number of variables, right? We don't have to restrict to 2. We're going to focus here on functions of 3 variables, so we'll call it t equals f of x, y, z. And we'll find the domain and range of a specific example. Okay, so we know that we have to make sure that A, the square root is defined, and B, that the denominator is not 0. So to make sure that 1, the square root is defined, and 2, the denominator is positive, or not zero, I should say. Well, no, yeah, not zero. Well, it's going to be positive because it's a square root. What are we going to need? We're going to need x squared plus y squared plus z squared minus 16 positive, or in other words, x squared plus y squared plus z squared is bigger than 16. So the domain is the set of all points outside the sphere center of radius square root of 16, which is 4, centered at the origin. The range, well, we can see that since the denominator is greater than 0 and the numerator is 1, which is greater than 0, the range is going to be the set of all positive real numbers. So functions of 3 variables, right, they're going to define curves in 4-dimensional space. And so we can't actually graph those. So 4-dimensional space, which we can't graph. So I'm going to say we can't represent them directly. But what we can do is use level surfaces to visualize, right? Because so to visualize these 4-dimensional things, we may use what are called level surfaces. So a level surface is super like a level curve. So a level surface of a function of 3 variables, let's just write the function. Well, I'll just write it of 3 variables. We'll call it f of x, y, z. Is going to be defined by the equation f of x, y, z is equal to c, for c being a real number, any real number. So for example, if I want to define the level surfaces, or level surface for the function f of x, y, z equals 9x squared plus 4y squared minus 36z squared equals, for c is equal to 0, what do? Well, I would literally just write what the level surface is. And give me one. Technical difficulties. Don't you love them? So the level surface is 9x squared plus 4y squared minus 36z squared equals 0. Or doing a little algebra, well, we could do a little bit of algebra, or we can recognize this as an elliptic cone. Which I took the liberty of graphing for you in Maple, just so you can see it. It's not the perfect graph of a cone, right? Because Maple doesn't like to do perfect graphs of cones, but just pretend that it looks something like this. All right, I'm going to stop here, but next time there's some suggested exercises, of course, and next time we're going to talk about limits and continuity. So have a great day.